start the session. So the topic is quantum AI, bridging the gap between quantum computing and machine learning. Uh, so the agenda is we look at the quantum computer and we look into quantum AI, quantum ML, and quantum AI cheat sheet. Cheat sheet is one-stop solution of all related terms with quantum AI, and see some tools and frameworks as of now. And then two pioneering visionaries in the field of quantum AI. No, one is quantum AI, this Google quantum AI, and second one is IBM quantum computing. And few look into challenges and some few resources and references. I'm a level based. I try to make this session as interesting and interactive and informative. Any queries can be posted now and then. And to begin with, this quantum AI or quantum computing and things, uh, the thing is radically a new type of computing. It's much like we are going for the first generation of computers, like classical computers. So it's still a long way to go. And with every technology which is more specifically called to be in its nation stage and beginning stages, we'll have some hypes, we'll have some implementation difficulties, chaos, depends upon socio-economical, market and technical risks, uh, and standard formation also. So in the stipulated time of 1.5 hours, as much as possible, I'll try to delve into these topics and give a bird's eye view and first view of the quantum AI.
Sir, sorry to interrupt. Slideshow mode, can you change it, sir? Thank you. Yes, sir.
Yes, now it is okay.
Yes, fine, sir.
So this is the agenda we're just going to look into. And I briefly, as I explained, it's in the beginning stages. A lot of if but else and what all kind of puzzles or we have some kind of clueless things and all these things. So the thing is that this is more of a philosophical thing. So this is about the idea. So the thing that differentiates scientists is purely an artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is probably that is sufficiently interesting, it's sufficiently difficult that it hasn't yet been solved. But the time for solving it has come now. So this is from Professor Savas Dimopoulos from Stanford University. Uh, so like with this, the we call a scientist called as Richard P. Feynman, who is called as the father of quantum computing. So from his words, nature is not classical, damn it, and if you want to make a simulation of the nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So with your permission, I'll just like play this video.
We have a very exciting last talk.
Video is visible?
Yes, sir.
Yeah. So I'll glimpse to it.
Coming up. Dario Gil will take us into a quantum world. Dario is the Vice President of Science and Solutions at IBM Research, where he leads math, healthcare.
So for the introduction of quantum computing, this is in 2017 a video, a view of 1.9 billions. This is by Dario Gil, the IBM research head, who has did 1,500 researches across 11 laboratories, led the team that built the world's first microprocessor with immersion lithography in 2004. I'll glimpse it together.
on quantum computing, but I'll try to make it, entertaining and hopefully easy to understand. I'm going to start with a reference to this term of beautiful ideas. And it came from hosting a filmmaker about 1.5 years ago in the laboratory I just showed you at the T.J. Watson Research Center in Yorktown Heights. And it was a filmmaker that directed this documentary called Particle Fever that I don't know if you've had a chance to watch, but I highly recommend it. It's about the team that was pursuing the discovery of the Higgs boson in the largest physics experiment ever conducted. And a major character in the film is a professor from Stanford. And at the beginning of the film, he said something that really captivated me. He said, the thing that differentiates scientists is a purely artistic ability to discern what is a good idea, what is most importantly difficult. That is the possibility to create quantum computers. If you look at how we have created the basis of the information revolution, and you trace it back to other beautiful ideas, like what Shannon taught us, to think about the world of information abstractly. If you look at, an old punch card and DNA, we've come to appreciate that both carry something in common. They carry information. And Shannon told us that this world of bits could be decoupled from its physical implementation. That was really interesting, but in fundamental ways, it went too far, leaving too much physics out. So here is two scientists that work at IBM Research. Charlie Bennett on the right continues to work in our laboratory and is an IBM fellow. And they asked the question at the time of, is there a fundamental limit to how efficient number crunching can be, computing can be? And when they asked that question as physicists, they ended up with a very surprising answer. And they found the answer to be no. It turns out that number crunching can be thermodynamically reversible. This led to an exploration of what is the relationship between physics and information. And there was a now famous conference that was jointly organized between IBM Research and MIT at Endicott House, where this topic was explored in more detail, and the plenary speaker.
So this is the beginning of the quantum computing, and I'll not go much into it. This is more into physics. The quantum computing as such, the technology as such, is kind of physics. For your knowing, even the greatest the software, the animation software called as Maya, and all kind of simulation tools, etc., all has its base from physics. So here it's a huge group of near about 40 to 45 physicists, 46 physicists on the Physics of Computation conference held at MIT in the year 1981.
Was none other than Richard Feynman. And Feynman proposed in that conference.
So this is the beginning. I'll just briefly go into this qubits, because that's the basic of your difference between a classic computer and the quantum computer. So here in classic computers, we have bits zeros and ones, either 0 state or 1 state. And with qubits, you have 0, 1 or 0 and 1, all combinations. And this basic qubit can be of multiple. So 8 qubits, 16 qubits, 32 qubits, 56 qubits. So this number of qubits increases the power of exponentiation. And thing is that if you have a brute force combination of some exponential, the classical computer cannot do all these things parallelly, but this quantum computers can do them in a single shot. Still, to do that single shot, you have some errors or practical difficulties, and the hardware implementation should go in a super cool state. So the quantums, the qubit doesn't mean to exist in a what do you mean by a conditioned environment? It needs higher level of what you call deep freeze kind of refrigerators needs to be done. So later we'll see that picture here.
That if you wanted to simulate nature, we should build a quantum computer. And I'm going to explain you what that means and how it's created and the problems that it will solve. But first, I got to tell you what is the fundamental idea. The fundamental idea, just like we have bits in the classical world that can be a 0 or a 1, in a quantum computer, you have qubits, which stands for quantum bits. Now, the difference is that there can be a 0, a 1, or both at the same time. That exploits a principle of quantum physics called superposition. And it sounds weird and crazy, but it's true. Now, to give you this unease that you should feel when you talk about quantum information and quantum computing, I'm going to give you a very simple example, a thought experiment that also happens to be true. So let's imagine that we're going to solve this problem. The problem involves you have 4 cards. 3 are identical. 1 is different. 1 is a queen. We shuffle the cards. And we put them face down. And the problem we're going to solve together is find the queen. We're going to be assisted by 2 computers. One is a classical computer. One is a quantum computer. So what we do is we turn them down and we load them into memory. So we use 4 memory slots. The cards are identical. We put zeros. The one that has a queen, we put a 1. Right? So in our 4 slots, we'll have 3 zeros and 1 is a 1. We load them on the 2 computers. Now we ask to write a program to find the queen, find the 1. How would it be done classically? You would go and pick a random number. You don't know where it is. You go, look under that memory slot, see if it's a 1. If not, you go to the next slot, and so on and so on. On average, it would take you the equivalent of 2.5 turns to find it. It turns out that with a 2-qubit quantum computer for this problem, you can always solve it in 1 shot. So
this is the basic difference. The way of the classic computers is we are constraining everything into bits or the combination of bits. Now with the level of qubits, if you are going to increase the qubits, you can have all possible exponential possibilities in a single stroke.
An easy feeling that you have now should be an explanation that quantum computer is not just about building a faster computer. It is building something that is fundamentally different than a classical computer. Now, a way to think about it, an abstraction of it, is that a quantum computer is always going to have a classical computer next to it.
So the idea here is that, like, for the representations, we have a quantum computer, and the input will be the same sample space, and the output will be one of the desired result. So as it like it's like staggering a computer, a classical computer in with a quantum computer, and then finally the result will be your classical computer. So that's what's been explained here.
Computer is going to allow you to do is to explore this exponential number of states, this 2 to the n, where n is the number of qubits that you have.
So this is the basic difference. We have the power of classical computers restricted by 2 to the power of 2 in exponential. Now here with n qubit, there is a possibility of 2 to the power of n parts or n combinations, and of it we can represent all these 2 power n combinations in a single stroke, and from that which one is to be taken can be taken by as one path.
So now we have relatively small quantum computers with few qubits, but just think of the number that by the time you have 50 qubits, you have 2 to the 50 states. That's a phenomenally large number. But in the end, after you explore this number of states, you go back to a classical output, a string of zeros and ones that you interpret with a normal computer.
So the idea is that basically it's a sequence. Finally, when you superimpose and supermap onto the result part, it will be just in a sequential classical strip.
So why is this interesting? And I think in this mean and why 2 to the 50 is a very large number.
So this story, everyone might be knowing that after the invention of the chess, the emperor wanted to award the inventor of the chess. And the person told that he wants a single grain with the first step and twice exponential with the next boxes. So what happens is the power of exponentiation. So it's after 1 month it is this many grains of rice. So that is after 1 month. And then after 64 days, it is 461 billion metric tons of rice. So this is to get to know the power of exponentiation. So this is what is that we are achieving, or this is what has been that quantum computers are trying to achieve, or more specifically look into. So this example, next, the typical example.
And you get. So there are a large number of problems in the world that have this characteristic that they blow up exponentially. And a dirty secret in the world of computing is that we obviously talk a lot about all the things that computers can solve, and can solve a lot of things. But then there's a lot of things that computers cannot solve. And very interestingly, they cannot solve it now, nor ever.
So this is basically the problem of Turing machine. So because Turing machine happens to be the basic of a classical computer. So the state, like anything which is constrained by the states. Later we'll see the types of problems which can be solved and the types of problems which are eliminated by the classic computers, and how which the quantum computer takes them as a candidate and is going to solve.
And the reason is because they have this exponential built into them. So take as an example this fairly simple equation, factoring. So if I have a number m that is made out of.
So this is a pretty encryption problem, a Shor's algorithm, which says that still now all the encryption technology has been proven, saying that you cannot factorize a prime number, a large prime number, into 2 primes. So the classical computer will take that many million years or so, and with the quantum computer it takes just 100 seconds.
The multiplication of 2 large prime numbers, and I only give you m, and I ask you find me p and q. It turns out sequentially by prime number encryption. Universal fault sequence what would take 4 as a problem to be possible. Take chemistry as a problem because it also has this characteristic that it blows up exponentially if you try to calculate it. This equation that you see here is very interesting because it's predicted to occur at the ocean floor near volcanic sites, and famously it's been hypothesized to be the basis of the.
So this chemical reaction happens to be has multiple combinations. Let's say it's the base of the ocean from where volcanic eruptions. We say that how these 2 ferrous sulfate and hydrogen sulfate form and then convert into carbons and kind of different types of things. So this infinitely larger number of exponential combinations, it's another candidate of quantum computing.
Sites, and famously. But if you take a molecule like iron sulfide and you try to do relatively simple calculations with a normal machine, it turns out that we're not very accurate. And the reason is that molecules form when electron orbitals overlap, and the calculation of each orbital requires a quantum mechanical calculation. So for that simple molecule, you have on the order of 76 orbitals, and 2 to the power of 76 is intractable with a classical computer, so we cannot solve it. Again, on this theme of or assumptions that computers solve everything, but they don't, If you look at calculating, for example, the bond length of a simple molecule like calcium monofluoride, we still get it off by a factor of 2, even using the larger supercomputers in the world. To me, this has been very interesting.
So here with the classical computers with the higher level of supercomputing or parallelization, but still there is an error or a difference between the calculation of bond length of simple components. So that it takes a 25 electron system, Titan, a 43 electron system, but no standard computer ever built could simulate a 50 electron system exactly. So this is the limitation in drug kind of molecular chemistry stuff.
This recognition of all these problems we cannot solve. This is of logistics. So true, this recognition of all these problems we cannot solve. It's also true in optimization problems that are the basis of logistics and routing and portfolio optimization. There's tons and tons of problems in which at best we do approximation.
So here is another kind of combinational optimization problem. These are can be taken as the candidates which has a tremendous limitation to be solved by classical computers, and the the quantum computers takes to be them in an easier or unimaginable faster lightning times. So encode decode problem, computer error and iterate. So this is the problem. The same thing we just here we take the problem, encode into the problem with the qubits, give it to the quantum computer, and then get the answer, and you're just going to decode the answer. So these assignment problems, closure problems, constraint satisfaction problem, cutting stock, integer programming, knapsack, minimum spanning tree, scheduling problems, TSPs, vehicle routing and rescheduling. So trivia, very complex and more time consuming in years and years with supercomputers are all can be the candidates for quantum computers. And here that the primary thing to me is still now the bottleneck or the problem more specifically is that like how to make this qubits, the fabrication of the qubit and qubit process, and we assume that in time as the time technology advances, so this time is the complexities or limitations are going to be taken care, and then we'll be able to see as much like we have PCs, we're just going to have quantum computers.
But we're far from optimal because the number of possibilities is enormous. So if there's one message I want to be able to come across is that we have this easy.
So this is the understanding we need to get to practically differentiate the problems. The inner core is the classical problems or the easy ones that can be done by classical computers. And the next one is your simulating quantum mechanics. That's your quantum easy. And then still you have your hard problems. We'll see that how the three are done.
Easy problems, which is the world where classical computers fit and the problems it solves. But then there's these other hard problems that go outside. And if you don't believe that P equals NP, which I would say the majority of mathematicians don't believe that that is the case, that those problems are hard for a reason, the only avenue to go and tackle that, aside from approximations, will be through the creation of quantum computers. So where are we? We believe that small practical quantum computers.
So a brief bit of looking into the qubit realizations of the fabrications. Very simple to get to know the understanding of quantum computers. This is going to be the base. So as we had your process with registers and gates of the classical computers, now excuse me. Now we're just going to see briefly about the building of your qubit.
Are going to be possible, and we're building them now. It requires reinventing the whole stack. The device is different. It's not the traditional transistors. As an example, this is the device we use for the quantum computers that we create at IBM based on superconducting Joseph subjunctions. And you're
so they're called as subjunctions, superconducting subjunctions. So these supercomputing subjunctions need to be maintained in very, very ice cold or freezing temperatures, so that they'll be holding the qubits with them. So this is the bottleneck or the choking or the problem for realization of the quantum computers.
Seeing an example of one of these devices is a superconducting device. And because it's superconducting, you have to cool it. So this is what a small quantum computer looks like. What you're seeing here is something called a dilution refrigerator. And this quantum processor sits at the bottom of this refrigerator.
So with classical computers, you're just going to have only the cooling fans inside them surrounding that processor. Now this quantum processor sits again in the refrigerator, the quantum refrigerator.
At the nice temperature of 15 millikelvin.
So that's 15 millikelvin. So that level of, so this is where is the, now we say that we'll have a newer, radical, groundbreaking, miniature size deep freeze systems. So that will make quantum computers tiny or nano, micro.
So that is colder than outer space, where we have to put this quantum processor in. This is what, for example, a 16-qubit quantum processor looks like.
So this is a 16-qubit quantum processor.
And inside you see the square where the qubits are, and you see these squiggly lines, which is this coupling.
So this is 8 and this is 8. So all put together is this 16-qubit.
Resonators that allow you to send the information and couple to the qubits to send the information. This is what the wiring looks like into the refrigerator going into a quantum processor. Is these coaxial cables, and because the way you send information to a quantum processor is through a series of microwave pulses that go in, and then you're able to take it out. Now, if you look at pictures of what computers were like, right, in the 40s and the 50s, it's kind of like where we are today, right? That's what, a quantum computer, that's the signal processing required to actually send all those signals down the coaxial cable.
So this scenario is exactly same like when we had the 60s, machines of 50s and 60s, larger machines built with diodes, vacuum tubes kind of things, and slowly how it has been evolved to now these tiny handheld systems.
Cables, it looks like that. But we've also seen this movie before, in the sense that we know how much progress we have made from those early systems. And while we don't anticipate that quantum computers will be on your phone, because they require cryogenic cooling, we definitely believe that access to quantum computers in the cloud will be something that people will be able to leverage behind the scenes, even not knowing. Because we believe that, we created a small quantum computer.
So we'll see this in later slides. This is research.ibm.com for quantum that is available. The quantum setup is there, which can be accessed over a cloud. So next one is the quantum application example with hydrogen molecule. And just like glimpsing here. And finally, this is the keynote of this is what is the father of quantum computers, Richard Feynman.
Discovery of what we can do and what value we can create. Interesting part, big problems we couldn't solve before. So I'll close with Feynman, who proposed this original idea of creating.
So this we looked in an idea about your quantum computers. Then we look into the IBM quantum computer, how it is exactly.
So this is it.
This is a quantum computer.
This is a quantum computer.
Here I am seeing a real life. So we're going low, and there were lots of areas that we just.
The thing that, so the quantum computer is a chip in this one here, but this whole thing keeps the quantum computer working at insanely cold temperatures like we talked about.
So this is all refrigerator technology.
So all of these cables that you see here on the side carry signals down through the fridge into the processor, and then they do their quantum stuff, and it comes up. And it goes to these room temperature control electronics, and they turn it into things that humans can understand.
That is a quantum computer. We were allowed to touch it, which was cool.
Oh my God.
So I think it's really funny that when people generally talk about like the difference between classical and quantum computers, people are like, okay, well, you know how a classical computer works, right? But like the truth is that like nobody knows that. A simplification of it is, so this is it.
Sorry.
So this is it. And bits are made out of pieces of silicon, and you have, you know, tens of thousands to millions of them in your computer. And they can either be in the state 0. You know how a classical computer works. Bits are made out of pieces of silicon, and you have, you know, tens of thousands to millions of them in your computer. And they can either be in the state 0 or 1. We call it the ground state or the excited state. And everything that you type into your computer, like all words, all numbers, all colors, get translated into computer speech. But it's very binary, right? A quantum computer is run on qubits.
Qubits aren't like bits. They aren't a 1 or a 0. They're more complex. Think of this like a wave. A qubit could be really likely to be 0, which means a lower energy wave. Or it could be really likely to be 1, which means a higher energy wave. And each qubit has a probability of being each. When a quantum computer is working,
As the control
those waves interact and then finds the most likely answer. If this is all confusing, don't worry. All you really need to know is that quantum computers calculate things very differently than classical computers do. And that makes them good at different things.
Quantum computers are not going to be faster at everything than a classical computer. Like, it's not good for addition, right? Because your calculator and your phone is perfectly good at that. But
So this is where the real stuff it's work. So Howard is just going to, like, if you take the wave, it is just represented, the entire wave is represented here. So that is highly, highly impossible with your classical computers. So with the qubits, this is the possibility. Fine. So moving to quantum A. Now, for the sake of understanding with A, artificial intelligence is the revolution. It's hyped up more with ML and AI kind of stuff. So now quantum AI is the symposium of quantum technologies to AI, are giving AI capabilities to quantum. So quantum computer AI or quantum AI is an emerging solution driven by quantum science. Quantum computers running AI could revolutionize numerous industries and fields. It's like a living genius, a superpower. The ability to analyze a vast amount of data, recognizing complex patterns, and make predictions to the level of accuracy and speed. So the 8 leading quantum computer AI companies, Google Quantum AI, Sandbox, AQ, Quantinuum, Xenadu, QLabs, Zapata, and Terra Quantum and Menten AI. Later, I'll show you one few of the commercial products and tools that are made possible the zeroth or the first generation of the quantum AI. So here is that we have seen basically what is quantum computing and how it is different from the classical computers. And now, still now, this quantum computing is seem to be a bit of a long way to go with standards, precision, stabilization, and whatnot, like the fabrication problems, etc. I have not went to the problems of quantum computing. We'll come to the problems of the challenges part later when we look into the challenge part. So I've given the link here, like which gives more insights on this quantum AI. It tells about how the quantum computing and AI are connected. So now we look into the quantum ML. So you can just like play this video which tells about quantum AI. Now this is quantum ML. ML and AI, that's again algorithms, the machine learning algorithms in a higher level, we call them as AI and deep learning kind of things. So here, this is machine learning, the ability of making computers think critically and rationally and take decisions as humans do. It's an act of mimicking the basic unit of brain cells. We call them as neurons. Now, how that is differing with the classical ML and the quantum ML. So here in a classical ML, the classical data is zeros and ones. So you have mathematical algorithms, you use either CPU or GPU, and then we go for pattern recognition. Now we say the classical data and classical things, we take the classical data, transform into qubits, and then this is the quantum data. So now there are only 3 bits in classical data. Now here you have 3 qubits. So that is, as I told you in the previous way, that you have the combination of qubits, the possibilities of qubits, 2 to the power 8 is n possible states. Now we get quantum data. So now, as we told, like everything, like we have your classical problems. When we went to parallelizing, there was again a need to convert the problem or the data into the parallel data. Likewise, when the one step, don't worry about the steps. Like later we'll develop some utilities and tools which have the ability to convert the classical data into quantum data. Now, till this particular point, it also seems to be, what do you say? Excuse me. It also seems to be a bit hiccup or a bottleneck. Now, here is that like, so this is your classical machine learning. Now, this is your quantum machine learning. So here, the classical data needs to be converted into the qubit data or the quantum data. And then the machine learning, classical machine learning also needs to be your modified to your quantum machine learning. And now the Q data is fed to the QML. And as you say, you have your pattern recognitions and learning kind of things. All these things happens. And finally, you get the results. So here it is that, like you say, the time is going to be reduced. Now in QML, so this is the quantum data, it's a qubit. Now we have superposition of states. And the pattern recognition is that we do a quantum processing. And as we seen in the previous case, with quantum states and qubits, it's possible to have all the possible combinations in a single array of a combination of qubits with an exponential combination. Then the pattern recognition happens to be at a thing. Now, the thing is that candidate applications is like face recognition, entertainment services, self-driving automation, finance investments, recommendation systems, and genetics. So like this is like a quantum machine learning is a field that aims to write quantum algorithms to perform machine learning tasks. So here is what like we are just going to convert the basic ML, classical ML into quantum ML and quantum things. Now, a study by IBM and MIT found that SVMs, the support with machines, are mathematically very similar to what goes inside a quantum computer. So here is where here to be more insistent on this particular thing is that like whatever thing which we do is a fraction or a part, one maybe a fraction of mimic of the nature. So that's why I say that like what we see in movies are creating scenes. Like we say that like think of the case that like we people have dreams, right? Will it be possible to capture our dreams? That is much like your quantum computers. So we parallelly have thoughts. Like now I'm handling this session. Parallelly, I'm just like one thread. I'm talking about my pending tasks. Parallel, I'm thinking about like what my better half does and what my daughter does. So all these things in a single strip, it'll be able to be held with quantum computation, Q states and qubits. So that's why I say that like SVMs and all these things, patterns and huge calculations which have uh, tremendous exponential 2 to the power of any number of n to the exponential combinations in a single stroke, and we take the pattern and just make it as a classic. So quantum machine learning allows scientists to take the classical ML algorithms and translate it into quantum circuits. So now the circuit also need to be modified for handling this machine learning. So it can run efficiently in a quantum computer. So this is the article. So here is how AI is transforming quantum computing. So this is the impact of machine learning on machine and deep learning in industry applications. So there is an experimentation of quantum and ML for route optimization and quantum and ML in pharmacology. And then this there is the possibility of error corrections in quantum bits. So that quantum error correction is also the part like the potential of AI in quantum error correction. This is the challenge in integrating AI with quantum. Now, the thing is that like the superpositions and entanglements could allow quantum computers to perform coordinate operations. These are all the thing is that the data representation, processing speeds, and hardware, the hardware circuitries of converting the CML into QML. So these are all the thing. So this Quantum AI Insider is one company that it is inventing the ecosystem builder. So it is in 2024, the QA, the Quantum AI Insider is into the Swiss tech builder called as Phoenix Technologies to further innovation and entrepreneurship in quantum technologies and AI. So this is still in what you call it is in nation states. Later we'll look into few of this tools, libraries, and platforms that are available. So here is one platform that's called as a K1 AI platform, an AI-driven platform that also provides end-to-end support services like QA, ventures, ecosystems. We'll come back here. So this is quantum AI and quantum ML. Now coming into what else other than things to be solved or to be experimented or to be realized for this quantum AI. So that's given as a cheat sheet. So the thing is that like it is an intersection of quantum computing and AI, focusing on how quantum computing will help this machine learning algorithms or enhance these AI algorithms. So first, like you have your qubits and Q gates and Q circuits. So this implementation. Then your quantum algorithms. So it provides all these exponential combinations representing qubits, the states, the logic circuits and combinations and holding them, all these stuffs together. Then your QML. So here we say all these conventional classical MLA techniques needs to be modified into the quantum versions. So SVMs, quantum SVMs. So the quantum version of SVMs that can potentially offer speed up for classification tasks. And neural networks. CNNs now are converted into QNNs. So the quantum neural networks. So quantum versions of neural networks that can leverage quantum parallelism and superposition. Then quantum principal component analysis. So QPCA. So quantum algorithms for dimensionality reduction that can offer exponential speedups over classical PCA. And quantum AI applications. So which are all the quantum AI applications? So the optimization problems. So which can be used to solve complex optimization problems more efficiently. Pattern recognition, quantum pattern recognition, so that can enhance pattern recognition tasks in AI. Then data clustering is also can be done using quantum AI data clustering. So it can improve the clustering algorithm, providing faster solutions to clustering problems. And the challenges as like the error correction, scalability, and integration. As it like both are very precision, complex, and highly emerging research fields. An integration of both this higher level of unprecedented technologies is your quantum AI. So look into the quantum AI tools and frameworks. Later we see so far the developed initiatives by Google AI, quantum AI, and IBM in the hardware part, the below quantum bit processor and its representation in SPIC. Briefly, we'll see with the available time. So we look into the quantum AI tools and frameworks as per with the open source domain. So here are some notable tools and frameworks in this domain. It's still in its evolving phase. Circu, it's developed by Google. It's an open source framework for creating, editing, and invoking noisy intermediate scale quantum circuits. It's designed for developing newer type of quantum algorithms and near-term quantum computers, and is written in Python, making it accessible to developers familiar with quantum. Then Qiskit, an open source quantum computing framework by IBM. Qiskit allows researchers and developers to build and execute quantum algorithms on simulated quantum computers and real quantum hardware. But now, still because these quantum computers are a bit complex systems and that not being able to be viable to be accessed by users. So there is a possibility of using accessing them over the cloud. So, so this Qiskit is an open source quantum computing framework. So it has robust set of libraries and has a strong backing from IBM, making it as one of the most comprehensive tools available. The TensorFlow, that's a very famous and popular ML AI deep learning framework. So this TensorFlow Quantum is the modification of TensorFlow libraries by Google to be fitting it with quantum. So TFQ integrates quantum computing framework like Circu into TensorFlow. So enabling the development of quantum machine learning applications. It supports both classical and hybrid quantum classical models. So now the thing will be in another remarkable high or the rise when two domains or two different variance things that are available. For case considering IP, the Internet Addressing Protocol, IP protocol, version 4 and version 6. Some few years back, there was a debate like the drawbacks of IPv4. We are depleting more number of IPs. So we go for a classless internet. We go for a higher level, 2 to the power of 64, 2 to the power of 128 IPv6. Then IPv4 and IPv6 will coexist. Then again, classical computers will be there and quantum computers will be there. The classical algorithms will be there and quantum algorithms will be there. So then they're like how these things converges, how these things are put together. So here is that like quantum classical models allowing for creation of applications based on quantum data and hybrid models like quantum CNN. Then your project Q. So it's a product, it's an open source. I've given all these links of these projects in my references later can be for more insights and to more curious delving into each of these subjects. I've been shared with the coordinator of the organization. You can be shared with. So this project Q is an open source quantum computing software framework developed by Zurich's project by the European Union. It allows user to implement programs in Python, the quantum programs in Python using powerful and intuitive syntax. It can translate these programs to be any type of backend, including simulators and actual quantum chips. Now, as with the thing is that like when we had this wireless sensor networks and kind of things when we are trying, when it is highly complex and costlier to develop and to simulate networks, we develop network simulators. Like again, another area of quantum AI is to simulate quantum chips and simulate quantum computers and make them as what do you call software versions or virtualized quantum computers or your cloud quantum, excuse me, cloud quantum computers. That is that, like it can translate, this project Q can translate the programs to any type of backend, including simulators and actual quantum chips. Now, Strawberry Fields, it's developed by Zonado Quantum Technologies. It's an open source framework for quantum or photonic quantum computing. The study of laser, IR, and optical chemistry kind of stuff, optical physics types. It provides tools for designing and optimizing photonic quantum circuits and includes quantum simulators built on NumPy and TensorFlow. Everything seeks to be Greek and Latin because since that, like it is a different set of world of plethora of problems and gates and all these in the states, we are not able to visualize, we are not able to be talked up more by and large. Then the next one is your Qiskit Aqua. So it's a part of Qiskit ecosystem. So it provides a suite of algorithms for quantum machine learning, automation, and chemistry. It is designed to be used in both quantum simulators and real quantum hardware. I've not looked into quantum simulators. If possible, when I'm just going to give this particular presentation with some added references and links, I'll just put them. Now here, it is just like I've did my level based of curating the best available and the limited available things on QA in this one presentation. Maybe with your curious learning and more of surfing and getting the stuffs with. I've not tried this hashtag with quantum AI also. I'll just like in some quick time, I'll just put them and try to consolidate them and put them here when I'm just giving the final version of my presentation. Fine. So far this is okay. Any queries? Is it okay? Is the pace is okay? Any participants? Any interactions? Any queries? Professor Pradeep, is it fine? Is everything is fine?
Yes, sir. Everything is fine, sir.
Fantastic. I don't get any query or any interaction from the. This is the problem with your online sessions, right?
Yes, sir. Sir,
So
actually, we
clueless.
have planned at the end, sir.
Fantastic.
After the
That's
session, if
fantastic.
in case. Okay.
It's fantastic. Okay. So far it is fine, right? I think things are fine.
Yes, sir. It's going fine, sir.
Thank you. Thank you. So the next one is your Pascal. It provides a neutral atom quantum computing device that can be programmed directly from CircuIt, offering a platform for developing and executing quantum algorithms and actual quantum hardware. Then Qiskit Nature, an extension of Qiskit. It focuses on translating problems in chemistry and material science into quantum circuits that can be executed in existing quantum platforms. It integrates with classical chemistry packages like Psi4 and Psi-SEF to generate and compile physics equations for quantum computers. So now we look into the Google Quantum AI. So because this is again this is where is one next leap into the quantum AI. So here is the thing is that like into quantum AI of Google. So Google's quantum AI is to build quantum computing for otherwise unsolved problems. This is their quantum processor called them as Willow. So Willow Quantum AI is the latest state-of-the-art quantum chip. It's a big step towards developing a large-scale error-corrected quantum computer. So there is a blog post, there is a paper, and there is a video on the spec sheet. I'll go through the spec sheet. So this is the Willow quantum computer, quantum processor spec sheet. It's released in December 2024. It's just 2 or 3 years old. So this is the latest quantum chip, features breakthrough improvements that enable major advances in quantum error correction and random circuit sampling. So these two are the benchmarks that we call it as if you develop any quantum computer and you run your quantum applications and you want to check whether this quantum computer is running properly, this is much like think of them as your benchmarks. People who have studied this earlier system, the computer system testing and kind of stuff, we have heard about your benchmark suits. Likewise, in for this, the error correction, the quantum error correction and random circuit samplings are the benchmarks to get to know the precision or the accuracy of your quantum calculations. So the number of qubits is 105. So the possibility of this below quantum A computer is a quantum computer is 2 to the power of 105 combinations. Unimaginable. So the connectivity is 4-way typical, the quantum error correction and random circuit sampling. So these are the specifications of the error correction for chip 1 and chip 2. And this is the qubit grid. So this is the qubit grid. So it represents the numbers inside the qubit, refers to the row and the column index, right? So this gives about the distributions on error correction and sampling and coherence. So this is the spec sheet. Right. So this is the roadmap of Google Quantum AI. So in 2019, it's just like only 5 years old. So they started with, is it visible? Is readable? The screen? Is the screen visible, ma? Is readable? I want to zoom it.
Yes, sir. Yes, sir. It is visible.
Do you want to zoom it? Is this okay, pretty?
No, sir. It is visible already.
Yeah. So it's in 2019. They started with qubit of 54, and the logical qubit error was nothing. And in 2023, they went for the quantum error correction. So the physical qubit was 10 to the power 2. The logical qubit error was at the rate of 10 to the power of -2 in 23. And the major milestone 3 is the physical qubit is 10 to the power of 3. And the qubit error rate was reduced to 10 to the power of -6. And the qubit is 10 to the power of 4. And qubit rate still remains 10 to the power of -6. And trying to scale up the physical qubit from 10 to the 4 to 10 to the 5, 10 to the power of 4 to 10 to the power of 5. You see this like the change of the qubits or the quantum chips evolving from phase to phase to phase, right? So 1, 2, 4, and then it's going to be 16, right? So the logical qubit error is 10 to the power of -6. And milestone 6 is large error corrected quantum computer. So the error rate drops to 10 to the power of -13. So this is the roadmap. So these are all the resources, things about the Coursera posts of quantum AI kind of stuff. So here you can just go through this quantum AI course from the Coursera. So it talks about quantum errors and quantum computing. So all these topics related to this quantum computing as a whole. So have it goes for the Google for Developers link. So this is the Coursera page for. So this is the quantum computer of Google. So this is the below hardware. And coming to the software part of the quantum systems, so the open source tools. So the CQ, I mentioned already. So you can directly go to this cloud form of CQ and QSIM. So it's a full wave function simulator given the GitHub repository. So this is the quantum simulator. And libraries are OpenFEMion, TensorFlow, Quantum, and QuizIm. And resources are the repositories Quantum Lib and Stack Exchange. I'll try to give these links for your quick reference, or else you can take from here. So the third-party extensions are PennyLane. It's the PennyLane CQ version, the CQ modified with PennyLane. It is integrating or connecting the PennyLane quantum machine learning capabilities with CQ. Alpine Quantum Technologies, it's a 3P extension. So, it's ion quantum devices which can be added. Then Pascal, it provides a neutral atom quantum computing device and can be programmed directly from CQ. So these are all the open source tools. From then the educational resources. This gives learning about these things. So the quantum, these are the courses that are available from Coursera, and it takes you to the Quantum AI lab, and it takes you to the educational videos and what is error correction and the qubit game. So they're giving an in-depth immersive into the game. So this is the educational resources part. So the documentations are there, and the publications. So in year-wise, hardly we get near about 44, 45 publications year-wise, year on year. So these are the publications that are available in Quantum AI. So you can refer all the articles from this link, and you can download and view them on link. So the more of the circuitry part and kind of stuff. So with this about the part with Google Quantum AI, and this is the Google Quantum AI's YouTube link. I've shared this also, the Quantum AI videos, the video shorts and the playlist, all these things are available here. So it has some 10 playlists which has all these things. So I've shared this particular link also to glimpse into the Quantum AI of Google. So then with IBM quantum computing, so IBM now this IBM quantum doesn't have Quantum AI, but still it'll be interesting to go into but to see into the IBM quantum computing. So this is IBM.com quantum or the quantum technology as such. So here also the quantum technology roadmap. So they also provide Qiskit functions, Qiskit SDK, and Qiskit serverless and Qiskit computers. So they provide on the cloud. So here also some inventing what's next in quantum. So then resources and then pricing. They give the quantum computers for simulations, cloud quantum computers. So in open plan, it's access up to utility scale computers from up to 10 minutes of runtime per month. And this is $96 US dollars per minute for IBM cloud of quantum computers, premium and dedicated softwares. So this is the thing. These are all the things that are available, and you can just see the catalogs. So it provides functions, Curie chemistry, singularity machine learning. So here this part is QA. So solve real-world classification problems on quantum hardware without requiring quantum expertise. And then your optimization solver, circuit functions, information management, etc., etc. So, so this is the IBM quantum platform. So this is your platform. like by signing it with an IBM ID, you can just get the IBM ID and then you can access the IBM Quantum at the cloud, right? So these are all the documentations, learnings, platform, and the courses, right? So that are available. These are the functions, the resources. So these are the QPUs, the quantum processing units that are available. So that can be taken. So there are 11 types of QPUs. It gives the types. It is a processor type. So it gives you the spec of all these things available. So this supports up to 156 qubits, and this is 127 qubits, and this is 127 qubits, and this again with 127 qubits. So you can. It's much like your cloud. How you go for an AWS and get your medium X and TX and kind of T1, T and X large machines. Like the same way here also it provides the the cloud forms of your quantum machines with the varying size of qubits. So I will leave the other part of explanation. Now I just like for the want of time. So this is so this is the brief of your quantum circuits and software and publications and related topics kind of stuff. So all these things goes here. It can this can give a more idea to newsletters kind of things. All these stuffs are together here in this link. So you have seen Google Quantum AI and IBM Quantum. Then coming to the challenges, the Quantum AI challenges is the integration of quantum computing and AI. There are challenges like error correction in quantum computing, algorithm development, scalability, training time and efficiency, integration with classical systems, ethical and societal implementations. Because as I told you, factoring the prime number defactorization was the only big relief that we said all the cryptographic algorithms we are using are safe. With this quantum computers, within seconds, they will break the factorizing problem. So that's again a big problem. Now, say you have your quantum safe encryption algorithms. That is again another way to be of making your algorithms quantum safe. So then quantum safe cryptographic algorithms. So now with quantum computing into the place, all the conventional systems need to be remapped or either to be made safe with this quantum. Right? So these are set of QA challenges. Then few of quantum AI resources. So this one is from the AAM. So here it says the Google says it's Alpha Qubit, AI system for quantum error suppression and scaling quantum computing. TensorFlow Quantum combines quantum computing and machine learning for hybrid machines. Quantum chemistry tools. So these are the versions from Google. And IBM is Qiskit machine learning and quantum AI. And NVIDIA comes with its own CU Quantum, allows AI researchers to simulate quantum system using NVIDIA GPUs. They also provide quantum AI frameworks. And Microsoft with QDK, the Quantum Development Kit. So I've tried to consolidate a few of the publicly available quantum AI resources. And this image is from the source, the Analytics India magazine, right? So this gives a picture of AI plus quantum and who are all the, as of now, with the four major players, Google, IBM, Microsoft, and NVIDIA. And I've given all these links. So these are all the references. And briefly, let me go into one particular company called as Quantum AI. So it is, as of now, it providing some commercial solutions to quantum AI. So the Quantum AI company, the quantum.ai is the link. I just added them in my references also. So this is the company. So they give these products, like each one can be seen here. So Q memory to develop room temperature warm RB vapor based quantum memory, photon level, and Q folio, it's quantum enabled portfolio optimization. EPS QKD, it's a quantum key distribution. As I've been talking about, the cryptographic algorithms need to be crypto safe, or quantum safe. So they provide quantum key distribution demonstration toolkit. So you can just follow this Quantum AI company Twitter or LinkedIn page for updates, or this particular website for their things. The qubit IQ, transforming data processing through quantum enhanced intelligence. So this is this CLAMS, empowering hospitals with AI-driven insurance claiming process. This lab AI using generative AI. So these are generative, and certain things are generative and certain things are quantum. So which things which has this Q has this quantum integration with them. So CheckQ, QS Leap, QMac, Q memory, Q folio pro, EPS QKD, and qubit LQ, right? So some of the commercial variants, cutting edge products by the Quantum AI. Fine. So I've given this link as well. So this is few of the references which gives more basics into all these things. And with that, like, I've come to the end of my presentation. Hope I'm not bored, and to my level best with the opportunity and my fortune of my search in this topic, and I've landed here. And again, I dedicate this session to all my elders, parents, well-wishers, and my teachers, with which I'm what here be witnessed. Thank you. And in bit, like, am I with the time?
Yes, sir. You're well within the time.
Fine. So now we have 8 more minutes, I'd say.
Yes.
Participants who would like to ask any questions can raise their hands to get unmuted, or you can put your queries in the chat.
So again, the concluding remarks which to be given here is that, like, with the past experiences we have seen with new type of things, we had seen something called as a grid computing, which never took off, and still we have metaverse. Still, it is struggling to be in the streamline as much. So again, in the beginning of cloud, when Amazon was developing, this Amazon went bankrupt, but now it managed. So all these things are possible only with viable solutions, and be able to be welcomed by the market, by and the large, and potential consumers, and the developments of standards bodies, and the leverage of making the miniaturization of the quantum process, etc., etc. So we hope for the best, and we think the quantum computer is next going to be a revolution. We wish and hope and pray that things will go fine. Thank you. Murli Bhaskaran Venugopal.
Yes.
Yes, sir. Your questions?
So you can unmute and speak, sir.
Unable to. Yes, ma'am. Sir, good evening, sir. Very informative.
Thank
One
you,
basic question, sir. The logical gates and qubits. You said qubits are 3 0 and 0, 1 or 0 alternative. Still,
Yes,
we are able to quantify. Well, logically, we know clearly if one bit is or 0.
so, Professor, your voice is not clear. You can type it. It's better. If it's possible, you can type your query. I'm not getting your voice is breaking.
So in the meantime, can we hear from Dr. Basant?
Yeah, please.
Can you unmute, sir, and
Yeah, good evening, sir. Good evening,
Very
madam.
good evening, Professor.
Yeah, sir, your presentation was very good and it was a nice topic and explained perfectly.
Okay.
So, my question is, sir, you have explained everything and it is the tools are available in Python, means which are compatible with the Python software. Is there any option which are compatible with the MATLAB?
With MATLAB?
Yeah.
Which ones? I'm not sure about what is MATLAB. I'm not heard of.
Okay, suppose whatever the quantum AI tools which are available, means the tools are available which are compatible with all the tools what you told, these are compatible with Python software.
Sir, they're built using Python.
Okay.
These libraries are built using Python.
Okay. So is it possible to run that software through means by using MATLAB software?
Of course, like sir, the thing is that like to understand is that like which are all the problems of MATLAB can be done in like again as I told you with your classical ML problems to be run in QML, it needs to be converted. Yeah, the MATLAB problem need to be converted to be run using Qiskit and the Q version of the simulation, whichever simulation you do.
Okay.
So like here, you see here, I've seen, sir, hope I've given you your answer, sir.
Yeah, I got means it is they built by using the Python. So it is also possible. Means concept is the same. We can use MATLAB codes or MATLAB tools also by using MATLAB tools. We can use the same.
Yes, sir. Here in this slide, you can see here it supports both classical models and hybrid model. So some libraries will support both.
Okay. We can use they are using the Python codes. We can also use using the same concept. You can use also the MATLAB codes.
Exactly.
Okay.
Thank you, Professor. Thank you very much.
Okay, thank you,
so
sir.
there is a question in the chat window by Professor Rajendra.
What's the question, ma'am? Can you read me, please? I'm just like not sure.
What about neuromorphic computing? Is it taking over quantum computing?
Neuromorphic is also in line with the quantum, sir. I thought of including it, but want of time, I've sorry, I've not took it. I'll just add the links. They are also in the hype of building neuromorphic also. Good question. Great question. Any other queries?
As of now, there's no queries, sir.
Okay. The MOC team, you have any queries, and your internal faculties, you have any queries?
Yes, actually very informative. These things that I'm a novice in this quantum computing field. So
Everyone, even the field is novice.
Okay, sir. So we have got very detailed information about in all the areas of the quantum computing.
No, I'll still more to add, like for want of the time, and also add to more things. Maybe I've tried my level best to make them coherent. Thank you.